Greetings and welcome to my new calculus channel. I am John Gabriel. In this video today, I'm going to discuss what exactly are the elements of Euclid. And I've talked a lot about this in the past, but this is a lot more detailed and there's a lot of material to cover. So I only have 15 minutes and let's see how far I can get. First of all, let's consider these questions. What are the elements about? What was Euclid trying to accomplish? Why did Euclid use diagrams? Did Euclid produce any constructions at all in the elements? Does the word axiom or postulate appear anywhere in the elements? Does the word geometry appear anywhere in the elements? Did Euclid acknowledge the concept of infinity? Are there any circular definitions? Are there any vague or obscure definitions? So, the elements, or in Greek stihia, are the de facto foundations of mathematics, not the rot that you hear of as the Zermelo-Fraenkel axioms or set theory, which is supposedly the foundations of modern mathematics. They're not valid, and they have never actually replaced the foundation of mathematics because they are not true science or true mathematics. So Euclid's main goal was to establish the science called mathematics, which is primarily about measure and number. There are no axioms or postulates in the elements. Okay? And please read this article. There's a link to it. Study it, actually. You'll need to study it. There are no constructions in the elements, and the elements is not about constructions. The word used is sistis ether, sistisas the, sistis as the, which means recommended. This was a manner of speaking in ancient Greek. To recommend means to put forward something or someone with approval as being suitable for a particular purpose or role. In the case of Book 1 and Proposition 1, the possibility of an equilateral triangle, a distance composed of three equal magnitudes, is to be considered. So Euclid chose to use diagrams to represent the abstract ideas of location and distance because it is much easier to explain the propositions and the conclusions, as you will see in an example shortly. None of the words axiom, postulate, or geometry appear anywhere in the elements. Did you get that? None of those words. And by the way, I'll place a link to this presentation so you can study it again in your own time. The Greek word requirement is incorrectly translated as axiom or postulate by Sir Thomas Heath. Euclid never acknowledged the concept of infinity, even though he used the word apiro, which in his context meant indefinite, not infinite. One must remember that he was a pioneer who was trying to write down all this information in a systematic and a logical way. He made some mistakes by using circular definitions and some which were outright obscure. Let's see a couple of examples. So, a good example of circular definition is the one found in Book 5 and Definition 1. A magnitude is part of another magnitude. Now, that is a complete no-no in well-defined definitions. Okay, you cannot refer to that which is being defined by itself. So the correct definition there would have been a magnitude is the concept of size, dimension, or extent. In other words, it's in its primitive form defined this way. Okay. And then an obscure definition is the one found in Book 7 and Definition 1, which is a shame because that's where Euclid introduces algebra and number and algebra. So he says a unity is that according to which each existing thing is said to be one. Now, the interpretation of that is really very, very iffy. But the correct interpretation is that an abstract unit is a ratio of equal magnitudes whose size is irrelevant. So Euclid was transitioning from measure through the use of magnitudes to measure through the use of numbers that are introduced as quantitative measure via the abstract unit with all the geometric arithmetic properties transfer to algebra, a weaker form of geometry. So the first 6 books are a prelude to set up the foundation for number, to introduce number, okay, and algebra. So for the example of these claims, let's study Book 1 and Proposition 1. So Book 1 and Proposition 1 says that we recommend that a triangle, a distance composed of 3 straight lines joined at their ends, each the shortest distance between any 2 locations, to be considered. So it has nothing to do with constructions. The diagram is there to make the communication of these ideas easier. So it says such a triangle is to be called equilateral. Here the notion of side is introduced itself as a distance being a portion of the complete distance. In other words, as only part of a triangular distance. Okay, so now that's not exactly how it's stated, and we'll get to the exact statement, but that's what was meant. And you have to remember that in classical Greece, communication was pretty much laconic. It was kept brief, precise, and to the point. And as I've said in past videos, often ancient Greeks would drop parts of sentences, either the subject or the object part, when it was understood by context what was being said. So that makes it difficult to understand even certain parts of the description of words. So for example, Greeks would refer to the word ευθεία without saying ευθεία γραμμή. Okay, and even today in Greece, if you ask for directions, they'll tell you, ευθεία, meaning it's a straight line, but they don't say line at the end. It just means go straight, the shortest distance. So without diagrams and named geometric objects such as straight line, triangle, and side, stating the first proposition becomes far more difficult, and that's even before the proof begins. So, given any shortest distance s, that is a straight line, a distance p is possible so that between different locations r, q, and t, along the distance p, the complete distance p, the distances between r and q, r and t, and q and t are all equal to the given distance s. Notice that we cannot use the concept of numbers since it has not yet been defined. Okay, so you cannot talk about distance between any 2 points or anything like that. It should be quite obvious to anyone with a modicum of intelligence that these diagrams were produced as, or were meant as a tool to communicate the ideas in this proposition. So what I've stated in here can only be interpreted like this. Okay, and these objects were already established through the 5 requirements, not the 5 axioms of Euclid as you've incorrectly learned throughout history. There are no axioms in sound mathematics, and Greek mathematics is sound, okay, unlike modern mathematics based on beliefs and axioms. So this is the only way that you can interpret this definition. So now the proof, and this proof here, I'm going to use words like circular, and I want to warn you that if we hadn't used define circle in the 5 requirements, this would be a whole lot harder to explain. So it says that the same circular distance is possible for circles whose centers are the ends of the same straight line. Since this straight line is called a radius, both circles have symmetrical arcs in each other's interior, meaning that they meet at opposite ends of the same straight line. And we saw an example of this in my article called There Are No Axioms or Postulates in Sound Mathematics. Again, the distance from either of these ends to the center is equal to the radius. So joining the endpoints of the radius to either end of the straight line, about which the symmetrical arcs are subtended, results in a triangle with all sides equal. So that proof is about as short as I can make it. But without naming the geometric objects or using diagrams, in other words, describing the proposition and its proof, would not be an easy task. So Thomas He said to construct an equilateral triangle on a given straight line. And in the Greek it says this, which is epitis dothesis ευθείας πεπερασμένης τριγώνων ισοπλεύρων Συστήσαστε. Okay. Whenever you see that over a letter, you have to place the accent there. So in English, it basically means on a given line of finite, triangle equal sides introduced. So to convince yourself, try to update the proof given on the previous slide without using the names of the geometric objects such as straight line, circle, and triangle. Also, you cannot use words such as side, since that presumes prior knowledge of the visual object used to represent a triangle. This is one of the simplest propositions in Euclid's Elements. Subsequent propositions become more complicated and therefore far much harder to describe without diagrams and presume geometric objects and their characteristics or attributes. Okay, so the Greeks had enough mathematics to produce a rigorous formulation of calculus. They didn't, but I did. And you can find that in my free ebook, which I'll place a link to in the details section as well, of this rigorous formulation of calculus. So yes, this proof here, if all these words were not predefined, like circle and straight line and what have you, you'd end up having a horrendous amount of words, which would be very difficult to understand. And so that's why diagrams such as these were used. And it's not about constructions, but the constructions were useful in convincing the students of mathematics about the ideas in the Elements. The Elements is not about geometry, by the way. It's a means of laying the foundations of mathematics, as I said right at the beginning. Okay, the Elements, the goal of the Elements was to establish the science of mathematics, and they couldn't have used something like area or volume or mass, because those would in turn require a lot of pre-foundations. Okay, so in other words, the easiest way to derive the science of mathematics from nothing was to use the concept of distance, which in its primitive form is just magnitude, i.e. the size, the concept of size, dimension, or extent. Very well, this is the New Calculus channel. I'm John Gabriel. Till next time, goodbye.